In this lesson, we're going to talk about mathematical expectation. Here's your first example. Suppose that an online sweepstakes is offering $10,000 to one lucky winner. All you have to do is watch an ad online to get an entry. I'd probably watch the ad. Why not? There's a chance at $10,000. So then 1 million people complete their entry, including you, and you would want to try to figure out, on average, how much money would you expect to win? That's kind of a weird thing to say. One person's going to get $10,000. Everybody else is going to get nothing. But hey, all they did was watch an ad. What's the harm in that? What the average would be is take everybody's winnings and add them together. You've got $10,000 plus 0 plus 0 plus 0 plus 0 plus 0. You're just adding a bunch of zeros. One person's $10,000 is averaged out among the 1 million participants who watch the video, and you'll find that we get an average of $0.01. That's not a lot of money, but if you only had to get 1 cent out of watching the video, hey, why not? That's not too bad. The question is, how much is your time worth? This idea is what we call expected value. Take each amount times the probability of that amount occurring, and I'll show you how that fits into what we did a moment ago. But then after we calculate all of these products, we will add them together. If you're looking at winnings, then this game is fair if the value is 0, meaning the amount that you pay is the amount that you're expected to win. If the value is positive, meaning you're expected to win more than you're paying, then the odds are in your favor. And if the value is negative, which is just about anything, then the odds are against you. Keep in mind that if the odds were not against you, then the people doing it would be losing money. Well, that's not something they want to do. So was this online sweepstakes truly fair? How much was your time worth to play that game? Just for an interesting comparison, let's suppose that the ad was 30 seconds long, and you got paid 1 cent. How much is that? Is that a lot of money for 30 seconds? Well, let's find out. Let's do a little bit of a comparison. If 30 seconds pays 1 cent, let's go up. That's getting paid 2 cents per minute. Now if we multiply that number by 60, that's getting paid $1.20 per hour. Is that really worth your money? Well, chances are the answer to that question is no. If you're only getting paid $1.20 an hour, that is well below the minimum wage. Now let's do a more complicated example. This time we've got 1 grand prize worth the $10,000, 2 second prizes worth $5,000, and 10 third prizes worth $1,000. Again, all you have to do is watch an ad. Now, what is the expected value if you assume there's 1 million entries, just like last time, but you can only win 1 prize? Here's how we will do it. $10,000 is the winnings that one lucky person will receive. The probability then is 1 out of 1 million in order to get that $10,000. But there's more. Plus, remember the expected value formula simply takes the winnings times the probability, and then we'll add them together. $5,000. Okay, $5,000 has 2 possible winners out of the million people. And then there's also a $1,000 prize that will be won by 10 people out of these million people. Now, if we calculate all of that out, we actually get this time that it is 3 cents. And if we use the same reasoning, we end up with $3.60 per hour, assuming a 30-second advertisement. It's still not really worth your money to do this, but hey, it's just watching an ad in your free time. Now let's look at an example that involves dice. You have to pay $10 to play this game. After you pay your $10, you roll 2 dice. If you roll double sixes, you win $50. If you roll any other doubles, you win your $10 back. If you roll anything else, you win nothing. You pay the $10 and you leave. What is the expected value of this game, and what are the expected winnings? Now there's a difference between the two. The expected value of the game is going to be the expected payout. whereas the expected winnings is the expected amount of money you will end up with over time on average when you play the game enough times. Let's take a look at how this works. At first, I'm going to ignore the $10. If you roll double sixes, you get paid $50. But what are the odds of rolling double sixes? Well, there's only one outcome for double sixes. You have to get two sixes. And if you recall, whenever you roll two dice, you have 36 possibilities. Plus, you have $10 if you roll any other double. That's actually 5 possibilities out of 36. Why 5? Well, because the double sixes were already used, so you've got the double 1, double 2, double 3, double 4, and double 5 left. If you roll anything else, you win $0. Now, we don't necessarily need to write this because we're multiplying by 0, but we've used up 6 of the possibilities, so 30 remain out of that 36. Let's calculate how big this is. When we calculate this, the expected value is $2.78. On average, that's how much money you would make from playing this game. But remember, you had to pay $10 to play the game. This is where the expected winnings come into play. To do expected winnings, take the expected amount of money that you would get out of the game, subtract the cost to play, and you see here we're about to go negative. You get negative $7.22. So on average, you would expect to lose $7.22 each and every time you played the game. Now let's look at an exciting game that most of you in our area should know, the Powerball Lottery. Straight from their website, at least as of the time of the recording of this video, is the odds of winning the various prizes and how much you would win, as well as the categories of what you need to do to get that. You match so many of the white balls, whether or not you get the Powerball determines what your prize is. We won't dive into how these odds are calculated, but we will look at your expected winnings. Let's suppose the current jackpot is $450 million, and the tickets cost $2, so what are our expected overall winnings? I went ahead and have this written in the slide to keep this a little bit easier, but notice what I'm doing is I'm taking each prize, the $450 million, which again is the jackpot, the grand prize here, and multiplying by the odds of 1 out of this 292 million number, which I have here. Plus, the next prize is the $1 million, which is here, times 1 out of that 11 million number, and so on. Then you have $50,000 for 1 out of 913,000, right here. And so on. You just go through and you write all these down, and we get that this comes out to approximately $1.86 in your winnings. However, this is your expected value. The expected money that you would potentially win was $1.86, but your expected winnings have to account for the $2 ticket. So your expected winnings would be $1.86 minus the $2 ticket that you had to buy, which is negative $0.14. You're very close to breaking even, and there's actually a time that you do. If the jackpot were to rise, the other prizes stay the same, but the jackpot continuing to rise means that this number would go up, and over time it would make the expected winnings higher to a point where this number could become 0 or even positive. Once the jackpot gets high enough, your average winnings, your expected winnings, are actually bigger than 0. So if you're going to play the Powerball lottery, only play when this is high enough. And by the way, if you're curious, the sweet spot is at $491 million. Let's do one more example. Suppose a family has 3 children. What is the expected number of girls? We actually talked about birth orders to figure out all the possibilities for boys and girls near the beginning of the course. And if you recall, we did so by drawing Pascal's triangle in some form. We sort of discovered it was Pascal's triangle in the process, but we got to somewhere over here. In the row that contains a 3, this is the family of 3 children. There's one possibility for all boys. There's 3 possibilities for 2 boys and 1 girl, 3 possibilities for 1 boy and 2 girls, and 1 possibility for all girls. Now I also want to point out that these add to 8. From there, let's make what we call a probability distribution table. With it being out of 8, the number of girls being 0, all boys that is, there's a 1 out of 8 chance. 1 girl, there's a 3 out of 8 chance. 2 girls also has a 3 out of 8 chance. And all girls has a 1 out of 8 chance. Let's do the expected value here. 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Again, I'm just taking the number times the probability plus the next number times the next probability, and so on. If I do this, my fractions come out to 12 out of 8, or maybe we could just write it as 1.5. 1.5 girls is the expected number of a family with 3 children. Now, what on earth does that mean? You can't have 1.5 girls. It's really a matter of an average. Let's write down what's really going on. Of all households with 3 children, the average of the number of girls in these is 1.5 girls. So basically, if you were to take every household with 3 children and ask them how many of them are girls, next household, how many of them are girls, and you add up all of those numbers, take the average among that, you would discover 1.5 girls to be the theoretical average in this circumstance.